Welcome to the deep dive. Today we're tackling a really interesting question, one that sits right at the heart of AI, actually. What makes intelligence truly emergent? Not just programmed like a checklist, but something that sort of arises on its own, self-organizes, adapts from simpler rules. Well, we're diving into a fascinating project today, an artificial life simulation. It brings these evolving AI agents to life right there in a detailed 3D world. And this isn't just some clever bit of code. It's described as a profound collaboration between software developer Lee Stripp and the AI model Gemini 2.5 Pro. It's built with modern C++ uses OpenGL for the visuals, which look pretty impressive, and has GTK-MN4 for its interface. That's a C++ library for GUIs, quite a piece of modern software engineering.
Absolutely. And our mission today for you is to really unpack how this simulation creates this miniature ecosystem, an ecosystem where these agents learn, they adapt, they evolve, all without explicit instructions on how to behave. So we'll dig into its pretty unique dual brain architecture, look at the different agent types living in this world, and then get into the evolutionary mechanics, what actually drives their intelligence forward over time.
Okay, let's unpack that then. The core idea here, as I understand it, isn't to hard code every little thing these agents do, right? It's about letting intelligence emerge. But, for listeners maybe thinking, how does that not just become chaos? How do you stop a system built for emergence from just, falling apart? What are the guardrails, so to speak, to make sure useful behaviors actually develop?
Yeah, that's a really crucial question. And the fascination, I think, is in the simulation's basic framework. It provides simple sensory inputs like spotting food or seeing a threat and couples that with a neural network for each agent. The magic, or the emergence, happens as complex behaviors arise. It mirrors biological evolution, really, through variation, random starting brains, mutation, and selection. Who survives and reproduces? Think of it like uh, giving someone Lego bricks versus a pre-built model. You give them the bricks, maybe some basic instructions, and see what city they build. Agents start with these randomized brains, and small mutations can happen when they reproduce. Those whose random setups and learned behaviors work best, they survive. They reproduce, they pass on those traits. So it's emergence, yes, but it's structured. It's guided by these architectural principles inspired by nature, leading to intelligence that's robust and adaptable, not just brittle, hard-coded rules.
Right, which brings us to what I think is maybe the most ingenious part of this whole design, the agent's brain structure. It feels like more than just clever design. It's like a hypothesis in action. It suggests that maybe separating the what the decision from the how the action could be, a fundamental pattern for building scalable intelligence. And this is where it gets really interesting. These agents actually have two distinct neural networks. Two brains, essentially, much like biological systems, often separate high-level decisions from low-level motor control.
Precisely. Yeah, let's start with the first one. It's called the lsRNN. That stands for Lee Stripp's Custom Recurrent Neural Network. Think of this one as the agent's high-level cognitive center, maybe even its emotional center in a way. Its job is simply to decide the agent's current behavioral state, and it chooses from a predefined list: idle, roam, hunt, or flee. So it's deciding the big picture goal, not the nitty-gritty of movement.
So it gets a simplified view of the world, just the key information, like mood indicators.
Yeah. Exactly. The inputs are pretty high-level summaries. They call it binned data. So energy level isn't a precise number. It's just low, medium, or high. Same for threat proximity. None, far, near, dangerously close, and how close food is. These summaries, these bins, get turned into what's called a one-hot encoded vector, which basically means it flips a single switch on for the current category, like energy, low, making it really easy for the neural network to process.
Okay, got it. And how does it learn which state to be in? How is it trained?
Right. So for training the state brain, they use a method called teacher forcing. It's kind of like teaching someone to dance by physically guiding their steps at first. There's a set of simple hand-coded rules in the code in a function called update state transitions. This function acts as the teacher. It dictates the correct state for a given situation. For example, if energy is low and food is nearby, the teacher says, okay, the state should be hunt. The lsRNN then learns to mimic this teacher through backpropagation. That's a standard AI learning process where the network adjusts its internal connections based on how wrong its predictions were, trying to get closer to the teacher's output. Eventually, like the dancer, it learns to make the right state decisions on its own based on the patterns it learned from the teacher.
Okay, so the lsRNN makes the big call.
Yeah.
Right, I need to hunt. But that intention needs to become actual movement in the 3D world. That's where the second brain comes in, the LS3DRNN.
Exactly. The LS3DRNN, Lee Stripp's 3D recurrent neural network, is the action brain. It's like the tactical commander executing the strategy.
So if the lsRNN decides what to do, the ls3drNN is all about how to actually do it in 3D space.
Precisely. It handles the precise 3D motion. And it gets much richer, more detailed sensory data to work with compared to the state brain. It gets things like normalized direction vectors, basically, pointers and distances to the nearest food, the nearest friendly agent maybe, or the nearest threat or prey. It also knows its own internal state, like its current energy level, normalized.
And you mentioned some specialized sensors.
Yes, two really important ones for navigating the environment smoothly. There's a boundary avoidance sensor. This gives a 3D vector pointing away from the edges of the simulated world. Super important to stop agents just getting stuck against a wall. And then there's a local agent density sensor. This outputs two values: how many friendly agents and how many hostile agents are within a small, sort of personal space radius.
Oh, okay. So that's crucial for things like flocking or just not constantly bumping into each other.
Exactly. It enables that kind of emergent social spacing and collision avoidance.
And the really critical link, I guess, is how the ls3drNN knows why it's supposed to be moving. How does it get the context from the lsRNN?
That's the state feedback loop. It's another input to the ls3drNN. It receives the current state IDL, HUNIC, whatever, from the lsRNN also as a one-hot encoded vector. This is absolutely key. It tells the movement brain the context for its actions. It knows why it should be paying attention to that food vector, for instance.
Right. Otherwise, it's just processing sensory data without a goal.
Exactly. It would be moving blindly. So with this context and all the sensory data, its output is a 7-value vector. 3 values dictate translation movement along XYZ axis, and 4 values represent a rotation quaternion.
Quaternion. That's a mathematical way to handle 3D rotation smoothly, right? Avoids issues like gimbal lock.
Precisely. It's a robust way to describe orientation. Now, for training the ls3drNN, it also uses a teacher, but it's a bit different. Instead of being taught a specific position to go to, which could be quite rigid, it's taught a desired direction of travel. So, for example, if the state brain, lsRNN, says the state is hunted, the teacher provides the normalized vector, the direction, towards the food. The ls3drNN then learns, again through backpropagation, to output those translation and rotation values that will efficiently turn and move the agent in that direction.
Ah, I see. So it's learning a more general skill, how to move towards a target direction rather than just how to get to one specific point.
Exactly. It's more robust, more biologically plausible, you could argue. It makes the agents much more adaptable in how they move around.
Okay, now that we've sort of dissected their minds, let's zoom back out. We understand the brains, these two networks working together. What kind of creatures do these brains actually power? You mentioned it's an ecosystem, so who lives there? What are the agent archetypes?
Right, there are two distinct types, creating a simple predator-prey dynamic. First, you have the feeders. Think of them as the herbivores. They only eat one type of food, vegetable. Their main drives are pretty simple: find food when they're low on energy and flee if they detect a predator. What's interesting is that you often see emergent flocking behavior. They achieve this just by having a tendency to follow other feeders when they're in the roam state. It's not explicitly programmed flocking, it just happens.
How do you spot them?
They have a deep blue base color, and it gets brighter when they have high energy and darker as their energy depletes. It's a nice visual cue. And a key point for the ecosystem: when a feeder dies, its body turns into a meat food source. This directly links their life cycle to the other agent type.
No predators, presumably.
Exactly. Then you have the predators. They're the carnivores. Their main target is hunting feeders. But if there are no feeders around, they're programmed to resort to cannibalism. They'll hunt other predators. Survival instinct, I suppose. They can also scavenge, meaning they'll eat the meat food sources left behind when feeders die.
So their logic is pretty straightforward, aggressive even.
Yeah, quite simple. Prioritize hunting feeders first. If none are detectable, hunt other predators. If no agents are nearby, then look for meat. And visually, they stand out with a yellow base color, which also brightens up when their energy is high.
Okay, so feeders eat vegetables, predators hunt feeders, and sometimes each other or scavenge. It paints a clear picture. But for this ecosystem to work, it needs rules, right? The environment itself, the food chain, how is that managed?
Absolutely. The environment has these two specific food types. Vegetable is the primary source, the base of the food chain. The simulation spawns it periodically, kind of like plants regrowing naturally. Then there's meat. This is secondary, and crucially, it's only created when a feeder agent dies. It doesn't spawn on its own. This sets up a really clear energy flow. Vegetable energizes the feeders, and that energy moves up to the predators when they eat feeders or the meat left behind.
So the predator population is directly dependent on the feeders if the feeders die out.
The predators will follow soon after, unless they can sustain themselves purely through cannibalism and any remaining meat, which is unlikely long-term. It creates that classic ecological dependency.
And how do they actually detect and eat things?
The simulation uses simple distance rules. Agents can detect both food and other agents when they are within 20 units of distance. But to actually eat food or attack another agent, they need to get much closer within 1 unit.
Right, makes sense. Okay, so we have the brains, the agent types, the ecosystem rules.
Yeah.
Now for the really exciting part, evolution. How does this simulation make the agents actually get smarter over time? Where does the evolving aspect come in?
Yeah, this is where it connects back to that idea of emergence and adaptation. It's essentially a genetic algorithm woven into the simulation's life cycle. It starts with genetic diversity. When the simulation begins, new agents aren't all identical. Their brains are randomized within certain limits. This includes things like the number of layers and neurons in that movement brain, the lsRNN, also the number of neurons in the state brain, the lsRNN, that can be anywhere from 4 to 32. Even their starting learning rates are randomized slightly, between 0.01 and 0.00005. So right from the start, you have this diverse pool of slightly different agents, a gene pool, if you like.
So it's setting the stage for natural selection to act upon this variety.
Precisely. Then comes reproduction. When an agent gathers enough energy, it reproduces asexually. The child is basically a clone, inheriting the parent's brain architecture, the number of layers, neurons, etc., and importantly, all the learned weights within those networks. But here's the crucial bit for evolution. There's a small chance of mutation. When the child inherits the brain, some of those weights and biases might be randomly altered, just slightly. This introduces new variations into the population. It allows the simulation to explore slightly different strategies, generation after generation. Some mutations might be harmful, some neutral, some might lead to a breakthrough behavior.
And that leads directly to survival of the fittest, right?
Exactly. Agents whose randomized starting brains combined with the behaviors they learn make them better at finding food, avoiding becoming food, and just generally surviving in that specific environment. Well, they live longer. Living longer means they have more opportunities to gather energy and reproduce. So they pass on their successful traits, their brain structures, their learned patterns, potentially tweaked by mutation more often. Over generations, the traits associated with success become more common in the population. The overall intelligence or adaptiveness of the agents increases through this constant cycle of variation, selection, and inheritance.
It's really Darwinian evolution playing out in silicon.
Pretty much. And there's a neat feature for tracking this. When the simulation ends, which usually happens when only one agent is left or they all died out, the system keeps track of that last survivor, the so-called alpha agent. It then prints out the key genetic traits of this alpha agent to the console. Things like its type, feeder, or predator, its specific learning rate, and the exact structure of its two brains. The layer and neuron counts for both lsRNN and ls3dRNN.
So that gives the researchers or anyone running the simulation direct feedback on what kind of configuration actually proved most successful in that particular run.
Exactly. It's valuable data. It provides concrete insight into which combinations of architectural parameters and learning rates tended to lead to long-term survival and success within that specific simulated ecosystem. It's like reading the genetic blueprint of the winner.
So bringing this all together, thinking about this whole simulation, what does it really tell us? What should you, the listener, take away from this deep dive? It really does seem to highlight the power of this emergent approach.
I think what's truly elegant here is seeing how complex, seemingly intelligent behaviors can arise from relatively simple rules and the interactions between agents and their environment. It wasn't directly programmed, it emerged. It really underscores, I think, the potential of emergent intelligence as a philosophy for designing AI systems.
And it feels very interdisciplinary, too.
Absolutely. It beautifully blends ideas from AI, from biology, especially evolution and neuroscience, and from software engineering. It's a compelling mix. And the fact that the developer, Lee Stripp, released it under the MIT license is also really important, I feel. It encourages others to take it, fork the code, experiment, build on it.
Yeah, that openness is great. It lets the community play with these ideas.
Right. It becomes a foundation for further exploration, a testament to open science and collaborative discovery. It invites everyone to participate. And maybe it leaves us with a bigger thought, a more provocative question, perhaps. If we can see this kind of complex, adaptive intelligence emerging from simple interactions in a simulated world, well, What might that suggest about the hidden rules, the underlying principles governing intelligence and life in our own vastly more complex universe?